Thank you very much. It's my pleasure to be here. I'm going to talk about cloud infrastructure attacks. So I think this starts with what I come from. So this is a red team engagement that we did like way back. It's an anonymized version, obviously, but it kind of gives the idea of like what attacks have looked like for decades. So like you attack the DMZ and you jump to the internal domain and you get the mainframe or whatever, right? But question is, what does it look like when we're in the cloud? So first off, we have some bad news that there is no cloud, but to be serious, we have, it's not only the computers, but we also have like a platform that's shared between everyone. We have the APIs, and yeah, I think it makes sense to kind of talk of the cloud in a sense, even if it feels like a buzzword. And we're going to go through a incident today, and it's like based on real incidents that we do at Truesec. So I'm like I said, a principal forensic investigator. So we investigate a lot of like attacks and so on. So this is also, just for the record, taken from several different incidents and so on and put together. So we try not to reveal the actual attack. But anyways, so we see a single factor log on. Obviously, that's not a good thing. You have a cloud account and it's has all this, like you should have multi-factor and whatever, right? The device is enrolled and it's in the EDR, there's no alerts really there, and we see that they have changed the user password. So I guess case closed, shortest presentation on the first yet. But of course, we should probably add timestamps to this. And when we do that, we see that the password reset happened before all of the other things. And that doesn't really make sense, right? Then a device was enrolled, and then we see that single factor log on, and we also see some security info added. We didn't really go through that, but I think it's an underrated persistence technique that we see time to time in Azure and other cloud vendors, where we have like a password self-service reset functionality, and if you add like a recovery options and so on, usually you need to have like multiple different factors. But if you add that, it's a kind of a cool persistence technique, really easy. But let's go into that first password change, okay? So we see that it was made by an account called sync_something. So that's not a normal, it's not the user that they changed password on, that's the user that invoked the password change, right? So that leads us to a hybrid cloud setup, because that would be the default account that's used in that kind of solution. But before we go into that, let's just give an overview of what I mean with a hybrid cloud. So you can use federation, and in a federated setup, you could have like, it's Okta or ADFS and that kind of thing. But the flow is generally something like this. So at least with ADFS, that's what we're going to go through now. So basically, the user wants access to a federated app. So it says, I want access. He says, no, you need to go to Entra ID or Azure ID. And, I'm going to mix these two up all the time. It's actually called Entra ID now, but if you, read the Microsoft documentation, it still says like Azure ID in several places and so on and so on. So as long as they keep mixing it up, I'm also going to keep mixing it up. And we're going to see what it's called after this presentation. But yes, so it says not here either, go to ADFS, and ADFS checks with Active Directory, and Active Directory validates the logon, and eventually it signs a token that says like, yeah, this is the user, blah, 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 and it's signed with a token that the ADFS server owns. The user gives that to Entra ID, and Entra ID gives an application-specific token, and eventually they can then authenticate and like, yeah, use the federated app. So what we saw here was like a chain of trust. And that chain of trust is kind of interesting, because if someone compromises the ADFS server, they can perform a golden SAML attack. And that is when they steal the token signing certificate and the private key, and then another key. And if you have those, you can sign your own tokens, right? And then you're just going to fly by all multi-factor authentication and all of that stuff, because yeah, you are the ADFS server as a threat actor now, right? But that's not what we saw in this attack, right? They did some kind of password reset. This wouldn't trigger a password reset. They would just be authenticated. So if we go on to the next one, we could check password authentication. That's the other option. And in password authentication, they go directly to enter ID. It asks you to enter like the username and password that's put on a queue, and the AD Connect server, which is on-prem, polls that queue. And eventually it's going to check with Active Directory, and then it's going to send a Boolean to enter ID, which says yes or no, basically, if the login is successful. And if it's successful, it says welcome back. But problem is here, same thing as the other one, right? If you own that server, you could do a skeleton key attack. So basically, you can patch the function that is going to validate the username and password. And you can change that and say that if the password is banana, let the user in. So there's actually like implementations of this. You have like AAD internals, for example. It's a great toolkit if you want to dig into different attacks in Azure Active Directory. So still doesn't really fit, right? Because there wasn't any, login and it just let through. It was a password change. So let's go to the next one. In the password hash sync scenario, they will sync passwords from the Active Directory, and then it will rehash those passwords to SHA-256 and add a salt, which every modern password storage should probably use something like that. But Active Directory doesn't for some reason, probably legacy reasons. But point is, if Enter ID gets all those hashes synced up, then it can authenticate the user all by itself at that point, right? So it just computes the same hash one more time. So will just let you in. So let's think about what is needed to make that sync work. So first of all, we need to have that MSOL account. It's going to be an account that syncs Active Directory hashes, does an AD sync. If you worked in a SOC, you might see a few alerts of an AD sync attack with that account. And that's common source of false positives, right? Because it's supposed to sync Active Directory passwords. And then it uses another service account to sync passwords to Enter ID. And that password of that account is kind of interesting because that account must have reset password capabilities, right? Because otherwise it can't sync hashes if it can't change users' passwords. So if you're able to dump that password, you can then change whatever password you want to in Enter ID. So if someone does that and they have an EDR on the system, you're going to see something like this in the EDR. And that's what we're seeing in this attack. So someone is trying to extract those credentials, and that's just before the password reset happens. And you also see that service accounts being used. So that service account, if you just look it up, it's just a normal account, kind of. But it also has this role, which is not a normal Azure role, but it's like an internal Azure role that you can't assign to a service account. But it contains a lot of interesting permissions. And it's not only to change passwords, but it's also to take ownership of applications and a bunch of other stuff. So, when you're able to extract that password, you can then do a bunch of other stuff. And on top of this, getting initial access, whatever, what we're talking about now, it's actually like a good example of how we see privilege escalation happening in Azure. So imagine that you have this one account that has this permission, which is to take over an application. Then you can enumerate all the applications and you can find some kind of backup solution maybe. And that backup application have a lot of different permissions because it needs to, read everything. It needs to update, whatever. And in this specific scenario, it has the role management directory permission, which means that if they're able to take ownership of that application, they could then authenticate, create an app secret, authenticate as the application that they now own. And with that permission, they can add their own user as a global administrator. So it's a pretty cool trick because this account that they extracted isn't necessarily a global admin, right? And if you do it the right way, you don't sync your domain admins to the global admins, but you have cloud-only accounts and so on. But here we see that they can actually use this extra step to take over the Azure Active Directory. And applications in Azure is kind of interesting because it's not only, that it's used to escalate privileges, things like that, but it's also a kind of interesting persistence technique, meaning that if you take over, if you get good access in Azure and as a threat actor, you want to keep that access, you can create one of these app secrets. And it's kind of hard to see those, Like you can see it in the audit logs when they're created, but after a while, like 90 days by default, that log record is going to be gone. And after that, it's pretty much, yeah, it's really hard to see it. You can like actually use the API in some way, and you can extract the CI creation date, blah, blah, blah. But point is it's a really good persistence technique that we see used time to time as well. Then, of course, like if they use this to escalate, you're also going to see that this user is now being added to the global admins group, right? But one thing, it doesn't really make sense, right? It's we said that the computer that did that log on was enrolled, right? And yeah, we actually saw in a real case where the threat actor figured we would be more stealthy if we log on from a compliant device. So they enrolled the device. What they didn't know was that they would then get a EDR agent pushed out to the threat actor's own device. So we get the full timeline of the entire threat actor's machine. And yeah, my colleague actually has a full presentation of just going through this timeline, and they use it to attack multiple different companies. And yeah, I guess it backfired a bit on them. So yes, let's draw this as that graph that we had before, right? So we have the first thing, we see like a dump exfiltration of secrets on the AD Connect server. Then they use that account to take over the enterprise app. With that enterprise app, they make themselves global admin. And then they, with that enrolled device, authenticate to Enter ID. And then they also use that app to exfiltrate stuff, right? Because it has delegated access to read mailboxes and SharePoints and so on, which we haven't really seen in any picture because it's not that fun to see, downloads. But point is that would be their like final goal, right? In this case. But yeah, if we're going to follow this attack, like they can't just magically appear on the AD Connect server, right? So how did they get there? Well, we see in the logs that it comes a request from a Jenkins server. So Jenkins is this like build automation service, right? When I talk to my colleagues who work with securing CI/CD pipelines, they say that, yeah, it's really rare that you use Jenkins, but when I work with incident response, I see Jenkins pretty often. And I think there's some kind of, collaboration, like, trend there, right? Where we see companies that suffer from a cyber attack use it, and companies that are working, trying to prevent and being ahead of things, or maybe using something else. Because Jenkins is not a bad product in any way, but it's a product that a lot of companies use because they are locked into plugins and things like that, or maybe they want to keep things on-prem and so on. So it's usually this like really big Jenkins server that is running a lot of things, and it's hard for them to maintain it. And Jenkins is interesting because it has this script console that if you have the administrator permission, you can basically execute any code on the underlying server. You can also dump all the secrets, of course. So yeah, we saw that in this case, actually. We carved like the file system and saw there was deleted files, which contain something like this, which is, all the build secrets. And in Jenkins, you need to keep a lot of secrets, right? Because that's the system, depending on how you use it. But it's generally a system that is supposed to sync all your code, push it to your production, push it to your test, push it to whatever, right? And all these container registries and things like that. So if you're able to dump that, then you're going to get a lot of secrets in the organization. So yes, that's an evidence of a Jenkins dump. And on the Jenkins server, we also saw a rat being used, and it tunnels the C2 traffic through Gmail. And this is nothing new, really, but I think we've seen this in a few cases, and I think it's a very interesting C2 technique, especially when we talk about cloud, because it's the threat actors using the cloud at this time. And the way this works is basically it uses the Google APIs on the compromised server and checks, are there any new drafts? And it keeps polling. Eventually, the threat actor connects to the same Gmail account, and it creates a new draft with a command. And the next time it pulls, it's going to find that draft. It executes the command, and then it adds an attachment with the results of the output of the command. So, I mean, we're talking about Gmail here, right? But we've seen this being used with Dropbox, where you can upload files. We've seen this being used with Slack, where they create like Slack integration, and then they can post messages and so on. I think this is a really clever technique when it uses the same cloud infrastructure that the company is legitimately using. So it can really melt into all of it. So if the company is using Dropbox legitimately, then using a C2 through Dropbox is going to be really hard to find in terms of like in the network logs, right? And from the other side, like when the threat actor connects there, we're really blind. So is this the most genius C2 ever? Not really, because if you need to get this working, they actually need to have an API secret on the customer's machine, which means that it's possible to connect into the Gmail account if you get that secret, right? But before you think about doing that, I know there's a lot of different ways to view this. The way I view it is that it's a really bad idea to do that. It's multiple reasons. One of them is that it's probably not the threat actor's Gmail account. They have probably hacked that account and is abusing an innocent person's Gmail. And there's legal, depending on what country you live in, I guess. But I think the major reason is that these companies, these service providers, are being abused by threat actors, right? And they really hate that. So if you provide them with evidence that someone is abusing your service to tunnel see-through traffic, they will most often collaborate with you. And then they will be able to, on their back end, track down maybe more victims and shut down the threat actor's entire infrastructure. So I think that's a really good way to handle that compared to, the more cowboyish method of just hacking the hackers, right? So I would strongly recommend that, but I know there's different views. But anyways, yes, we have a C2 going through Google Cloud. Next question is, how did they then dump the Jenkins server, and how did they get that, like rat onto the Jenkins machine? Because that can't happen by itself, right? And we see that this old Jenkins server had Docker containers running all the builds. And someone at some point had figured that these build containers need to have internet access, and they need to be able to access internal services and all sorts of things. And they put them on the Docker default network, meaning that it is able to connect back to the Jenkins interface. So it's a fairly simple container breakout, right? You just use the network to connect out to something else. There are a few things here, right, that's missing. So one of them is, how did they compromise the container then, would be the next question. And we see quite a few ways that could happen. And this is a fairly cool way. It's called dependency confusion. We see here in a log that Python pip, so the package manager in Python, is downloading version 999.9999. That is something that exists in the public PyPy repo. But thing is that that is an internal package that they are hosting in their internal PyPy repo. And if you use this extra index URL parameter, it's going to try to find the latest version. And if there's a newer version with a name collision in the public one, then it's going to download that. So, if you have your company name package.blah, blah, blah, and I register that in the public repo with a newer version number, then pip is going to download my dependency instead of your dependency. This is very old, but it's something that is still a problem, because they say that you shouldn't use this. You should use index URL instead if you don't want to, use the public repo. But who wants to download the entire PyPy repo? No one. So everyone keeps using this old one, which is designed to be insecure. But it's not a great situation. Speaking of this parameter, another attack we saw, which was kind of cool also, is that this isn't a CVE, but it's a remote code execution in pip. So way back, which is like 2017, if you use this extra URL parameter, it made a clear text request, and then it was upgraded to HTTPS, which means that we saw a threat actor that had compromised network infrastructure in the middle, and they were able to then send the wrong packets back. And since this isn't a CVE, there are still like a lot of Docker containers and things like that is still using this old vulnerable version, because they don't really update stuff, right? And so basically what we saw was it gives this 403 or what's the SSL is required, and it's kept doing that, and then all of a sudden here's your package on port 80, and then it kept doing requested. So basically just picked a package and intercepted it. So a third way that we can compromise a container would be if they have the CI/CD configuration next to the code, which is kind of common, right? So if someone compromises the source code repository, they could change what runs inside the container, right? A third one is that, fourth one would be that if you're using a runner server that is shared between multiple different projects, then you can have like, because usually you have like protected branches and so on, you can't just commit and change things. But if they're sharing the infrastructure, then maybe you can create your own repository that's going to be pushed and run on the server, then break out, take over the server, and then wait around there for an interesting job to come. That's not what we saw in this case, though. This is what we saw. We saw a push to the GitHub repo, and it didn't have the CI/CD config and so on in it, but it had this requirements file. And within that pipeline, it runs pip or requirements file. So what they did was that they changed the normal name of the package to a GitHub URL of the package, which was like a fake of that package. And the only thing that changed is the setup.py, which is going to run when you run that command, right? So it's part of the installation. So it's not going to affect anything in the production and so on. It's just in the installation. And that created this, reverse C2 through Gmail as well. So we see that this comes from someone compromising GitLab. And then they take over this container right, and then they break out to Jenkins, and then they jump and eventually reach Azure. So there's still something lacking here, right? Even if you're able to reach the network of the Jenkins application, you can't just become administrator all of a sudden. You need to have that account. So how did they get that account? And what we see is that they were able with that first one to compromise a cloud VM in GCP, meaning Google Cloud, which is what the production and the development and so on environment used. So what do a threat actor do when they compromise one machine in Google Cloud? Well, there's this very interesting configuration in Google Cloud, which is that if you just do click, 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 click when you install a VM and don't change the defaults, it's going to use a service account which has kind of high privileges. One of them is that it's able to read buckets, meaning that if you're also uploading backups with sensitive data to buckets, someone who has compromised one of these machines can dump that service account and then access the buckets and get the secrets. That means that after getting root on one machine, they're then able to get secrets to another machine maybe, and then jump along in the environment. And by curling like the metadata, you can get how it's configured. Another way that we also see is these cloud tools. So if you're a cloud admin or like a developer maybe, then you recognize all these, Azure, AZ, and it's AWS CLI, and it's G-Cloud, something. But it's like these command line tools, right, that everyone uses to manage cloud environments. And when it comes to this, it's, you do this init, and then it saves credentials, and these are stored on systems. So basically what they're doing is that they're dumping these secrets, and they're just stored in like a SQL database, right, or a SQLite database. So if someone has remoted into a GCP machine, used their high privilege account, then they can get that account. And I think this is very interesting because, this is kind of the same thing that we're seeing in an on-premise environment, but we're seeing this in cloud. And this comes like, in the normal on-premise environment, the Active Directory, we see like, jumping between hosts and so on by dumping LSAS, blah, blah, blah. In here, we see kind of the same problem, but it's just a new version of it, right? So that would be how they got that credential. So basically, they jumped around, they found new credentials, they jumped to the next machine, found new credentials again, and then jumped and jumped and jumped. Eventually, they got an account that's admin on Jenkins server, and then we know the rest from there, right? So now we just have the last one, right? So how did they get into that GitLab machine? So they have multi-factor, so it should be hard, right? Well, we see something in a lot of incidents, which is called infostealers. And infostealers is this kind of malware that just spreads all over the place. And it's kind of focused on secrets on your computer. So some of them just dumps these secrets, it uploads it to some server, and then removes itself. So that's the only point of these kind of. And, your browser cookies, which gives you a session into your machine, they should kind of be protected, right? Well, this is kind of a one-liner almost to dump that, right? Because you need to decrypt, it's protected with DPAPI, and you're supposed to use them. So they're going to be decrypted fairly easily. Another one is Office app tokens. We don't, it's not that hard to dump tokens from an Office application. Just do a memory dump and then grep for the token, and you're there. So you would get some kind of alert for this. And I think this is kind of good that we're starting to pick up. And it's, if your token travels in an unexpected way, we're going to see things like this. And some tokens were actually better at protecting, which I'm really glad about. Like Windows 11 has this TPM requirements, right? So your primary refresh token is protected in TPM. But if it's not, then it's super easy to dump that refresh token, and then your account is really, really screwed. But yeah, so just to summarize up the attack, so that would be that you have this infostealer campaign, right? And the threat actor is actually different threat actors, right? Like one of them would then do the initial access, sell the initial access to the threat actor that then jumps into the GitLab and takes it from there. So, you remember that they enrolled the machine, right? I think this is an additional evidence that they're using infostealers. We actually see them browsing Russian market, which is like a marketplace for that on that machine. And finally, how did that redline stealer get into the machine in the first place? So before you panic and see that Microsoft GitHub repository is compromised, which someone pointed out, a competitor was very happy to point that out. Bleeping Computer did a bit more digging and realized that there is an interesting feature in GitHub, which is that if you start a comment on an issue, you can upload a file, and then that file is going to be hosted under the repository. GitHub didn't think this was a problem, but it's kind of a problem, right? That you can kind of make it look like they're hosting stuff where it's not supposed to be hosted. So if you want to have my slides, I took the liberty of hosting it in the official GitHub documentation. And with that, thank you.
All right, so we have some time for questions. If people have questions, please come up to the mics. Also take a little bit of time to fill in the survey in the app so that Alexander knows how well you like this talk. Please take some time to it because he took quite some time building the slides coming up here. Yeah, we have one question, Greg.
Yeah, thank you very much for the talk. Well, you really showed a complex attack scheme. This means that attackers were really interested in getting into the network of this organization. However, did you find out which threat actor was it who attacked the organization and what were its goals? Was it to deploy ransomware or was it cyber espionage?
The goal of the threat actor is my mic on. No, it sounded a bit weird. Sorry, the goal of the threat actors was definitely espionage.
Okay, thank you very much. And you didn't attribute it?
The attribution can't share, unfortunately.
Okay. Thank you.
Thank you.